First, between 1.2 and 1.5 grams of an unknown solid is transferred to a 250 milliliter beaker. Here, we obtained approximately 1.3 grams. Next, 30 milliliters of deionized water and 12 milliliters of 3 molar hydrochloric acid is added into the solution, and then it is stirred with a glass rod for several minutes. Note, all the solutes should be dissolved after stirring. Afterwards, the solution is transferred into a 100 milliliter volumetric flask. To avoid trace residue being left over by the solution, both the beaker along with the glass rod is rinsed 3 times. Then, the previously collected washings is then transferred into the volumetric flask. After rinsing, we may now add deionized water into the volumetric flask up to its calibration mark. Using a small portion of the unknown solution in the volumetric flask, we will rinse a 25 milliliter pipette. We will then proceed to pipette 25 milliliters of the unknown solution into 3 separate beakers. We will then measure out approximately 75 milliliters of 0.1 molar hydrochloric acid and add it into each beaker separately. The next step is to add 5 drops of methyl red indicator into each beaker.
Then, 25 ml of ammonium oxalate solution was added into each beaker while stirring. Approximately 50 grams of solid urea was weighed out and added into each solution. Each beaker was covered with a watch glass and placed on a hot plate. Over time, as the urea breaks down, the solution becomes more acidic, causing the indicator to change from red to yellow. Next, the respective solutions are filtered separately through a weight funnel using suction. Then, the beaker alongside the stirring rod is rinsed with approximately 3 ml of ice-cold deionized water and poured over the filter. This is repeated 2 more times. Afterwards, the filter paper containing the precipitate is transferred to the watch glass. Dry the precipitate in the oven overnight.
We retrieve the sample and collect the necessary data. After conducting our experiment, we will use the gathered data for analysis. For beaker 1, the mass of calcium oxalate obtained was 0.8 gram. Using 8 molar mass, we converted this to moles, giving 5.48 times 10 to the power of negative 3 mole. Next, we multiply this value with the molar mass of calcium to determine the mass of calcium present in 25 ml liquid. Because the unknown was diluted to 100 ml, we multiply by 100 over 25 to obtain the total mass of calcium in the entire sample. Finally, by dividing the total mass of calcium with the original mass of the solid sample and multiplying it by 100 to obtain a weight percentage of 58.59%. This is repeated for the 2 other beakers. The mean standard deviation and relative standard deviation was calculated both manually and also through Microsoft Excel, both of which achieving the equal result. The mean is 55.14, the standard deviation is 4.74, meanwhile the relative standard deviation is 8.60%. This is considered moderately high and show noticeable variation around the mean value. This also indicates a higher degree of uncertainty. Inconsistency may be due to poor handling of the experiment. In conclusion, the percentage of calcium obtained from the 3 trials did not produce an ideal relative standard deviation, as trial 2 differ noticeably from trial 1 and 3. This suggests procedural errors were present in at least 1 trial. Improvement in technique should be implemented to yield more precise results.
There is done. Now that the representative from South Africa has been mined